Okay, so welcome everyone to the last session. I'm Xiangrui from Databricks. So I'm going to talk about Spark MLlib. So it's a machine learning library on top of Spark. So at Databricks, I spend most of my time on this MLlib project on contributing new features, review pull requests, and help users on the mailing list. So today I will focus on the development side of MLlib. But since this is maybe a very new topic or new library, so for the first half, I will spend some time on general Spark and MLlib. And then for the second half, I will talk about new features in MLlib and what's the long-term goal of MLlib. So before we started, I want to thank everyone for voting this talk as the community choice of this session, the future of Hadoop. So I think the first question I need to answer is, well, what is MLlib? So how many people have tried MLlib before? Well, that's really great. So it's, the percentage is much higher than my previous talk. So yeah, MLlib is a Spark component focusing on machine learning. And the initial code contribution was from Berkeley MLlib, and the same as the creators of Spark. So it shipped with the Spark distribution since version 0.8. That was September last year. So MLlib is a really young project. It's now about 1 year old, less than 1 year old. But since then, we have 40 contributors, and this number is increasing rapidly. I think for 40 contributors, it's even more than some top-level Apache project. So for machine learning algorithms, for classification, we cover linear SVM, logistic regression, and naive Bayes and classification tree. For regression problems, we cover generalized linear methods, just like so linear regression with L1 or L2 penalty, that's Lasso and Ridge. And we also support regression tree. And for collaborative filtering, we implement a matrix factorization algorithm called alternating least squares. And we also support non-negative constraints, that's non-negative matrix factorization. And for clustering, we implement a very scalable version of kmeans. And then for decomposition and dimensionality reduction, we support principal component analysis and SVD. So that's the list of features in MLlib. But the question is, why I want to recommend MLlib? There are so many machine learning libraries out there, right? So let's take a look at, for example, scikit-learn. So this is a list of features. Who can tell the difference between this one and the previous one? So basically, this is what you see if you open a machine learning textbook. That's the table of contents, right? So it doesn't help say MLlib should be the choice. I think the first reason I want to recommend MLlib is that it is built on top of Spark. Spark is a fast and very general engine for large-scale data processing. I think so it can run programs 100 times faster than traditional MapReduce jobs. Because it can store the data in memory, and this is especially useful for machine learning applications because for machine learning algorithms, usually we need to do many iterations over the same data set. And if we need to load the data sets from disk for every iteration and serialize the data out after each iteration, it's very expensive. But even for on-disk operations, Spark also can be 10 times faster than traditional MapReduce. And for Spark, we provide different APIs in Scala, in Java, and in Python. And if you were here yesterday, you know there is also a project called Spark R, which provides R interface to Spark. So for Spark, the goal of Spark is really to make make life easier for data scientists and data engineer. So for the current technical stack, so I think there's still something between, well, maybe a very long distance between people who want to know data and the data itself. So the purpose of Spark is want to just make people get closer to your data and easy for them to examine your data and extract value from your data. So to achieve this, we try to provide very well-documented and very user-friendly APIs. And we also provide standard components, just like MLlib. We also have Spark SQL for SQL queries, and also streaming for streaming process, and GraphX for graph computation. And Spark itself is very friendly to the Hadoop ecosystem. Spark doesn't have any storage layer. It can read anything that Hadoop MapReduce can read. HDFS, S3, local file system, well, that's easy. So basically, everything you can provide as a Hadoop MapReduce input format, you can load the same data into Spark. And also, we make Spark can be deployed in multiple modes. You can run Spark on your laptop. It's very easy. And you can set up a standalone cluster with some HDFS support. And you can also run Spark on top of Yarn. So we support to build Spark with different Hadoop versions, 0.2, 1.0, and run with Yarn on major Hadoop distributions. So there was a huge amount of effort to make this happen because there are incompatibility between Hadoop versions and Yarn versions. So, and the biggest feature of Spark is you can store your data in memory and to avoid serialization and deserialization, and then make your analysis faster, and so you can get the answer quicker. Let's take a look at the Hello World example for big data. It's a word count. So for word count is you read your text files in, and you split your text file into words. And for each word in the MapReduce framework, for the map stage, you send a word as a key and set 1 as the value. And then in the reduce stage, you will collect the key value pairs with the same key and sum up the values, so you get the count per word. So let's read this code. First, I call sc.text file. Sc is a Spark context, and it reads a file here from HDFS. And then for each line, it becomes a RDD of lines. RDD stands for the resilient distributed data sets. It's a basic concept in Spark. So for each line, I apply a function that's for line.split and with a space as delimiter. So basically, it split the line into words, and I do a flat map. So each word becomes a record. After this line, we got a RDD of words. And then we map each word to a key value pair. And finally, we do a reduce by key. And the function is underscore plus underscore means sum them up. So it's very easy, but think about how do you implement the same program in MapReduce, maybe the Java API. So you need to do a lot of boilerplate stuff. So you need to override, let's say, override the mapper and override the reducer, set up the input paths as a part of Hadoop configuration, and how to run it as a MapReduce job. So, but you take a look at here. Basically, this is the code simply describes the algorithm. There's no boilerplate code here. So it's very simple. And let's jump to machine learning. For machine learning, the Hello World example is, let's say, gradient descent. So for gradient descent, given a loss function, you need to compute the gradient, the sum of the gradient of each individual loss. So here is some example code. So I load the text file, load the data in text format. And then I apply a parser to the data. So I get a list of feature vectors, a collection of feature vectors. And then I say I start iterations. For each iteration, and we call a map function. For each feature vector, I will compute its gradient, and then apply a reduce function. The reduce is taking the sums. And after this line, we get the gradient, the sum of the gradient of individual loss. And then we apply the updates. So that's very easy. But it's basically the same as if you write the code in MATLAB, right? But let's take a look at what under the cover. First of all, this is a parallel implementation of gradient descent. So when you load the data in, and Spark will know how to distribute the data to different executors. And then when you call a map, and the map stage actually is done in parallel, and the reduce will be done first on each partitions. And after we get just the partial sum of gradient on each partition, and the driver node will collect all the partial sums and do the final sum on the driver node. So, but you see, as a developer, actually, you don't need to know those details. And also, Spark can help to handle fault tolerance. So let's say if an executor died during the computation, Spark will try to find another executor to do the same task. And also, if an executor, maybe it's a struggler node, is very slow, and Spark will launch another executor to do the same task, which one finishes earlier, and Spark will take that and kill the other. So, you don't need to care about those details. And the real magic is actually inside the first line. And I mark it right, it's called .cache. So that means I want to cache this data in memory. See, for this example, I have many iterations over the data. So by calling cache, the data will be saved, stored in memory between iterations, so you don't have to reload the data. So Spark is really easy. It's suitable for machine learning applications. But the problem for this implementation is, it's not very efficient in terms of performance. It will create some temporary objects, something like that. But we take care of it. So we implement those algorithms and provide some user-friendly interface. For example, this is an example code for kmeans in Scala. And you read some data in, and you pass the data into feature vectors. And then you can call kmeans. Say, for this training data set, I want to train a kmeans model with 2 clusters and within 20 iterations. And then you can compute the cost and you do prediction. Just 4 lines of code. Also, it's very similar in Python. Python supports lambda functions. So for each function is simply just a lambda. So a few more lines of code, but basically the structure is the same. We also support Java interface. In Java, you need to define some function object, which maybe sounds like some boilerplate code. But we also support Java 8. In Java 8 supports lambda functions. So it's very easy to use the Java 8 to call this kmeans method. Also, we can combine different techniques together. For example, I have an image data set, and I want to do a cluster, but the dimension maybe is so huge. I want to first do a dimension reduction using principal component analysis. I can say just do principal components for the top 20 components, and then I do a dimension reduction by project the points to that subspace. And on that subspace, we can do a k-means. So still just a few lines of code. And this is parallel, that handles fault tolerance, and the data is in memory. Also, another example is on the collaborative filtering. You have some ratings and you want to make recommendation. And you just need to load a data set of user ID, product ID, and its rating. Then you call ARS for alternating least squares to train a matrix factorization model. And then you can do prediction and you can save those models. So that's one reason. So it's built on top of Spark. Spark is easy to use and very concise API. So the other reason is it ships with Spark as a standard component. So it is part of the Spark distribution. And there are other components I mentioned, Spark SQL, Shark, and streaming and GraphX. Those are all standard components of Spark. So the bottom graph is I search for Spark on Google Trends. You see, Spark is really becoming extremely popular today, and the project itself is really taking off. So what's the benefit of being a standard component of Spark? First is the community. So Spark community is the largest in the open source world. So right now, since the beginning, we have more than 190 contributors, individual contributors, and we have 50 plus companies contributing to the project. And I also count the discussion threads on the users' mailing list. And there were about 400 threads for the past month. So also, while Spark has a very good community, all those questions were answered, most of the questions were answered just within 1 day. So even inside a big company, you send some tickets to some departments, you may get it back maybe 2 days, 3 days, right? So, but those people are not paid. So it's open source community. Also, the Spark project is the most active project in the Hadoop ecosystem. So I look at the Jira. So for Hadoop Apache projects, they'll use Jira to track the features and track bugs. So for Spark, well, for the past month, it's about 300 Jiras created and 200 Jiras solved. And for MapReduce, it's 30 Jiras created and 228 Jira solved. I also checked the Jiras for Yarn. For Yarn project, well, I think it's about maybe 100 Jiras created and maybe 60, well, Jiras resolved. So let's go back. So what does it mean? So from a user's perspective, basically the user can get MLlib. So from the standard Spark distribution. So if they have Spark installed, they just need to say import MLlib. Then they get all the functions provided by MLlib. So also they can look for support from the community, let's ask questions and get answered quickly. For developers, this means if you contribute to MLlib, actually you can ship your implementation directly to the users. And also think about the maintenance. So if you want to maintain a project, actually you need to spend a lot of effort, right? So maybe someday you are traveling in the middle of nowhere. So then user may ask questions and no one can answer. So, but for this, you can take leverage on the Spark community. And it's very good community and it can take care of the users. So the next reason for being part of Spark distribution is unification. So I want to say a story here. So maybe I want to go out for dinner today. And I want to look for a restaurant and then make a reservation. Then maybe I need to know how to drive there. And if the food is good, so I may take a picture and submit it to social network. So you know what my question would be. So which device I will use? I will use my smartphone, right? So I won't use yellow pages for looking up restaurants. So how to do that? So maybe I need to do some bisection search, so for a particular restaurant. And the information may be outdated. So then after, how to do the navigation? So maybe I can use a dedicated GPS unit, but I won't do that. Because if I search for the restaurant, it's in my smartphone, I can see its address. I just click that address and I switch to my GPS app. So I can navigate easily to the restaurant. So I don't need to enter the address manually to the GPS. So at restaurants, what if I have a professional camera? It can take really good pictures. Perhaps I won't use it, because the purpose is just put the photos on social network. And if I use a professional camera, I need to take the photo and unplug the SD card and plug it into my computer, log into my social network, and publish the photo. In my smartphone, well, the picture quality may be not that good, but well, that's my purpose, right? I just need a single click to share the photos. So in the big data world, it's the same story. So think about the offline data pipeline. It's a very long data pipeline. It's starting from maybe user activity collection. You want to create logs. And after logs, you have this ETL jobs. You want to create databases, and you want to store those, process those logs. And after that, maybe want to extract features for your machine learning application and do some feature transformation. Machine learning is just a component of this pipeline. And after you train some models, you also need to think about how to make recommendations, whether you want to serve the model online or you want to do recommendations offline. So it's a really long pipeline. And think about if you use different libraries for each component, and you need to learn different languages, or maybe the same language but different APIs. And also you need to learn the data formats, how to connect each component, right? For this component, it may output Avro data, and the next component takes maybe JSON data. So you need to think about those schemes, how to make the scheme compatible, and how to upgrade. So last thing is you need to learn these different tuning tricks, because, well, for big data, if you want to make it scalable, you need to first understand your problem and then understand the system. So then you can make it run well and make it run scalable. So that's really hard if you have different libraries for different components. Think about maybe you have tried Pig. Pig is provides some nice language for data manipulation. But if you want some advanced features, for example, for the word count, what if I want to count backgrounds? So I want to put two words together as a single record. Then maybe I need to write a UDF to do that. And then when I implement UDF, it's totally different language interface. I need to learn a lot of Java. I need to learn the internals of Pig to implement that. So that's the cost is really high on this context switch. For Spark, so we have those standard components. They integrate really well with each other. I want to show some examples here. This one is how to integrate Spark SQL with MLlib. Basically, you may have some activities, for example, user subscribe or user unsubscribe a service. And you want to join this event with some user profiles, user feature database. And you can make a query in Spark SQL. And after that, you get some result. The result is still RDD. So the RDD is the fundamental concept in Spark. So since it is RDD, I can transform easily into the data MLlib can recognize, and then we can train a model and make predictions. No data is serialized out to disk in this example. So, and you just need a simple map from the Spark SQL table to MLlib training data set. And since Spark does everything in a lazy way, so it doesn't have some temporary storage or temporary data sets in the middle. So also we can do streaming. If you were here yesterday morning, so you have already seen this result. Examples, we can do some kmeans clustering, and then we can monitor the tweets. And from a specific cluster, and then you can see the tweets within maybe certain topics. It's very fun to try this example. Also, we can also do graph X. So you can do this graph computation. Maybe you want to do a spam detection. You have this content features. But since you already have the graph, maybe you want to try PageRank as an additional feature, a network feature, graph feature to your training data set. And then you just use GraphX to compute the PageRank, and then add it as a feature in MLlib and train a model. So it's very powerful. So also, besides those points, MLlib is also, wait. Okay, right? So let me say that. So MLlib is also actually comparable to or even faster than some specialized large-scale machine learning libraries. And I'm not going to show the result here, but if you are interested in, please come to the Spark Summit. We'll have more talks about MLlib and show the performance comparison. So in MLlib's implementation, for performance, we really care about one, performance and scalability, and users, whether this is user-friendly, and what's the cost of maintenance, since this is an open source project. Next, I want to talk about the new features in this 1.0 release of Spark. We released Spark 1.0 on May the 30th, maybe just a few days ago. So for MLlib, we added a lot of features, but for MLlib, so we provide some updated new user guides and some code examples as template to build applications. And we guarantee API stability for the 1.0 branch. So we added sparse data support. Also, we include a new scalable implementation of decision tree. We also have the data models for distributed matrices and SVD PCA. We support LBFGS. Also, we have this utility functions to do binary classification model evaluation. So we spend a lot of effort just to make our user easy to get hands-on. So that's why I start with the most user-facing features here. For the user guide, we use the contents are more organized in 1.0, and we separate code examples into tabs. So before that, we have this code examples mixed in the documentation. So people will see a paragraph of code in Python, and then, well, a next paragraph is Scala, then get confused while this cannot be read in the Python language. So now, this is now here. Okay, so you can visit our website and see the updated user guide. We also provide some examples under the Spark distribution for you to use as templates to build your own application. So this is one example here. So it just exposes those parameters, and it's very easy to use. You can submit your job in command line to Yarn, to standalone cluster. Also, we follow Spark core to guarantee binary compatibility for the 1.x releases and on stable APIs. We also have some experimental APIs and developer APIs. And we will provide aggregation guide between releases if there are break changes. So I want to use the rest of the time to talk about maybe big features in 1.0. The first one is sparse data support. So at graduate school, once I wrote this large scale, that's my major, large scale sparse linear list squares in a paper draft. So my advisor just crossed out the word sparse. And he commented, well, a large scale already implies sparse. So you don't have to mention sparse twice. So that's true. So Spark data sets are almost everywhere in the world of big data. So it may come from different resources. For example, if you do feature transformation, you want to turn a categorical feature into binary features, and then the feature dimension becomes the number of categories, and it's maybe really huge. So there are many places you can gain sparsity. For example, we can take a look at the Netflix data set. Well, it's very sparse, and it has only maybe a little bit more than 1% of non-zeros. And also, well, it's very popular data sets for binary classification. It's even more sparse. It's even less than 1%. And if you store the data in dense format, actually take about more than 200 gigs. But if you store it in sparse format, it's just 600 megabytes. So in Spark MLlib 1.0, we support sparse input data in all the 3 language APIs. And we also take advantage of sparsity in storage and in computation, in linear methods, kmeans, naive Bayes, and summary statistics. Basically, the computation time is linear on the number of non-zeros in your data. So this is how we store sparse vectors. Basically, if you have a dense vector here is 1, 0, 0, 0, 0, 0, maybe 3, and we will only store its non-zero indices and non-zero values. So for user, you need to think about how to recognize the sparsity pattern in your data. And for developer, when you implement the algorithms, just think about how to take advantage of sparsity on the storage complexity and runtime complexity. So here is one example. So I use kmeans to train a text data set. It has 12 million examples. The feature dimension is 500. So I compared sparse implementation and dense implementation. So you see sparse implementation saved about 40 gigs of storage, and it's also 4 times faster than the dense implementation. So sometimes it's really common, you cannot really store your data in dense format. So because it's so huge, it has to be done in sparse format. So I will skip the implementation here, and we also mention how to take advantage of sparsity in linear methods. That's logistic regression, linear SVM, LaShu, those algorithms. For sparse data support, I want to especially thank David Hall, who is author of Breeze, and Sam Halliday, who is author of MLlib Java. So those packages provide the fundamental linear algebra operations inside MLlib. So there are many other who joined the discussion when I implemented sparse data support. And the next big feature in this 1.0 release is a scalable implementation of decision tree. So we support both regression and classification, and continuous features and categorical features. So we basically, for information, for the impurity, we support Gini impurity and entropy. And for regression, we support variance as the information measure. So it scales well on very massive data sets. But if you want to know the detail, please just come to Spark Summit. Since the author of this decision tree implementation is Manish, he's going to talk about the details about it. So check the Spark Summit website to see the schedule of this talk. So there are certainly more features to explore in this 1.0 release. And they have, for example, we have this binary classification model evaluation. So you can, after you train a logistic regression model or you train a SVM model, you can compute the ROCs very easily to evaluate those models. So next, I want to talk about what is beyond 1.0. So for the next release is a 3-month release cycle. So basically, the next release will happen by the end of August. And for MLlib, so there are many features are going to this release. First of all, we want to standardize the machine learning interfaces for machine learning concepts, like problem, formulation, algorithm, parameter set, and models. So in this way, by standardization, we can build a good ecosystem around large-scale machine learning. So people can have their own machine learning algorithms, and as long as they are compatible with those interfaces, they can use other components in MLlib. Because MLlib is an open source project, you cannot just take all the algorithm into this project. So we want to try to build this ecosystem. And also, we want to support multimodal training. So basically, no one just train a single model. We often train just multiple models with different set of parameters. And we want to support that in a very scalable way. And also, we want to provide some utilities for statistical analysis, like standard hypothesis testing, sampling, and bootstrapping. So a lot of new features are coming, and let's just skip this page. So maybe there are many machine learning algorithms are coming to this 1.1 release. And I leave an empty bullet here because this is an open source project. Maybe you wake up in the morning and you see a big pull request adding some new algorithm to MLlib. So it's also interesting. So beyond this release, for the long-term goal, so I want to talk about what to expect from the community, or maybe you can join the community as a user, or maybe as a user and developer. First, we want to include well-known and well-understood machine learning algorithms. Well, there are algorithms well-known, but poorly understood. So you need to learn a lot of tricks to tune the system. Well, this is not what we want. We want this one to be easily used by users. And we want to maintain the documentation and APIs. So if you are new to machine learning, so you can also help us on documentations. And if you are expert in Python, and then maybe you can help to maintain the Python APIs to make it, just consistent with Scala APIs. And we also want to provide better integration with other components of Spark. For example, we may want to provide model updates, predictive model updates with Spark streaming. So for the long-term goal, we really want to address a practical feature pipeline. So that includes feature transformation and model evaluation. So even on how to serve models. So the last page of my talk is the contributors from this open source community. Maybe I'm missing someone here, but it's already many names there. So if you are interested, first of all, do check the Spark Summit. So it's coming in the end of this June. And so check the Spark website. And also there are tutorials hosted by Berkeley MLab called MCamp. There are some hands-on tutorials, very nice. And also you can check the GitHub page, see the developments, and join the user or dev mailing list to join the community. Thank you. So, question?
So I have a question about the algorithms, basically the classification algorithms that you mentioned. Is there fundamentally any reason that boosting methods were not included in the already existing and the roadmap?
Yeah, I think the reason is MLlib is really young. So we spend a lot of time trying to set up the infrastructure. On top of it, I think it's easy to implement those boosting, those ensemble measures. For example, we have the decision tree implementation. You can build random forest on top of it. So, well, it's just some feature we need to think about. Yeah. Oh, sorry.
Hi. What is the roadmap for ML optimizer or ML base?
Can you repeat that question?
Yeah. What's the roadmap for ML base?
So MLbase is currently a research project at Berkeley. So I don't know its roadmap. So that's what I can kind of answer that question. Sorry.
Yeah, I'd like to come back to your first example of gradient descent and about the aggregation. So if I understand correctly, each worker is sending its gradient to the master.
Yes.
And then if you have like thousands of workers and millions of parameters,
Right.
wouldn't you have a bottleneck during the aggregation?
There is a bottleneck here. There's a scalability problem here. I'm working on just implement some tree reduce algorithms. So you can aggregate first two together, and then you have a log p complexity instead of linear time complexity. That's a good question. More questions? Oh, for your question, I didn't hear clearly, sorry. Were you asking some text mining libraries?
Are you planning to include some of the text mining?
For text mining, basically, for the next release, we have this LDA algorithm. It's in code review, but I'm not sure whether it will get into 1.1, so, but we're working towards it. Yeah. More questions? Okay, thank you.